Welcome back to Cosmic Drift, where we listen to the whispers of the cosmos, where every visitor who stops by leaves us a gift. Sometimes that gift is a story, and sometimes that gift is a question. Tonight, we will contemplate both. In our previous journeys, we welcomed 3i Atlas, a messenger of ice and light, an ancient comet that awoke and told us its story in a brilliant blue hue. It arrived as a familiar traveler. Though from a distant world, it spoke a language our science could understand. It followed the rules we already knew. It brought us the comfort of knowledge, the peace of the familiar. But before it, and before 2i Borisov, there was the very first guest, a traveler of a completely different kind, a presence that swept through our world in silence and left behind an even greater silence, the silence of unanswered questions. Its name, given by its discoverers in Hawaii, is Oumuamua, a name that means the first scout from a distant place, and it was indeed a scout. But the message it carried remains a mystery to this day. Tonight we will place these two stories, these two memories, side by side. On one side, 3i Atlas, a beauty that can be explained, a symphony of astrophysics that we can appreciate. And on the other, Oumuamua, an anomaly that defies every assumption. A piece of music written in notes we have never heard before. One is an answer, the other is a question. We will explore the incredible differences between them, from their shape to their behavior, to the legacies they have left in our minds. We will consider the ideas, the hypotheses put forth to try and understand the wonder that is Oumuamua. We will do this carefully, with the curiosity of a child and the humility of a scientist. This is not an investigation to find a final answer. This is a meditation on the diversity of the cosmos. Let this video be a safe space for contemplation. There are no sensational claims, only deep questions. Let us listen together to the silent dialogue between these two travelers, one who came to reassure us that we are not alone in our familiarity, and the other who came to remind us that the universe still holds countless things beyond our imagination. So right now, allow your mind to open. Take a deep breath in and exhale slowly. Be ready to enter a journey of comparison and of humility. The story of two visitors and the lessons they bring begins. Before we step into the realm of the unknown, let us return to the familiar. Let us take a moment to repaint the portrait of the third traveler, 3i Atlas. It is not just a starting point. It is our reference point, our lighthouse of understanding, helping us navigate as we face the deeper mysteries. Let us together remember the story of the messenger of ice and light. When 3i Atlas was discovered and its hyperbolic orbit was confirmed, one of the first questions scientists wanted to answer was, what is it? And the answer came rather quickly and clearly. 3i Atlas was a comet, an interstellar comet, but a comet nonetheless. And in that confirmation, there was a sense of relief and familiarity. Comets are old friends of our sky. They have been observed and recorded for millennia. They are entities that we as a species are used to. We know their nature, the dirty snowballs of the cosmos, primordial blocks of ice, formed from the leftover materials of a star system's dawn. They are time capsules, fossils preserved in the deep cold of space, and 3I Atlas fit this description perfectly. It was an ancient relic, molded from ice and dust, in a distant cradle perhaps under the twilight of a red dwarf star. Most importantly, it behaved exactly as a comet should when it was far away, in the darkness of interstellar space. It was just a dormant, icy nucleus, but as it entered our solar system, as it began to feel the warmth of our sun, it awoke. The process of sublimation began. The ice on its surface transformed directly into gas, releasing a vast cloud of gas and dust. It grew a coma, a hazy and beautiful glowing shroud. The existence of this coma was the first irrefutable proof that it was an active comet. It was not a dry, barren rock. It was a living, breathing world of ice. This halo grew to an enormous size, larger than our own planet, a tenuous but majestic cloud. And then it grew a tail. The solar wind, the stream of charged particles from the sun, blew against the coma, pushing the gas and dust behind it, forming a glowing ribbon that stretched for millions of kilometers. Observers were able to see both characteristic types of tail, a curved, creamy white dust tail, and a straight, faint blue ion tail. Everything fit the textbook. Its behavior was like a visitor to a foreign land who speaks the local language fluently. It followed the rules. It interacted with its surroundings, with the light and the solar wind, in the ways we had predicted. It did not hide its nature. It introduced itself clearly. I am a comet, and in that clarity, there is a profound beauty. It showed us that the laws of physics and chemistry, the same laws that created the comets in our solar system, are also at work in other distant star systems. It was an affirmation of the universality of nature. Imagine you are listening to a piece of music composed in another galaxy. You might not recognize the melody, but you would still recognize the notes, the chords, the laws of harmony. 3 Atlas was such a piece of music. Its melody may have come from a strange place, but its structure, its very essence, was deeply familiar. It was a whisper from the cosmos, telling us, you are not so different. What happens in your home also happens elsewhere, and that is a comforting message. It builds a bridge of understanding. Across the interstellar void, it makes the vast alien universe feel a little closer, a little more like home. That is the portrait of the familiar, a messenger of ice and light, a beauty we can understand and appreciate. Hold this image in your mind, the image of a typical, beautiful, and explainable comet, because we will need this familiarity as we prepare to step into the shadow of the strange. The familiarity of 3I Atlas did not mean it was boring, quite the opposite. Within that familiarity, it gave us one of the most beautiful shows the sky has witnessed in recent memory. It sang a song, not with sound, but with light, a song of deep blue. To understand this song, we must return to the moment it awoke. As it drew closer to the sun, a remarkable event occurred. Its brightness erupted unexpectedly. It didn't just brighten, it blazed. This told scientists that it was an extremely active comet, a world of ice releasing its energy with great power, and it was within this outburst of activity that the secret of its color was revealed. When we look up at the night sky, we often see comets that are a faint white or slightly yellow. This color is mostly due to dust particles in its coma and tail reflecting sunlight, much like how dust in a room becomes visible when a sunbeam passes through. But 3I Atlas was different. Its coma, the glowing shroud around its nucleus, emitted a brilliant turquoise blue, a color that was vivid and intentional, not a random reflection. It was like a ghostly cosmic flame, a turquoise gem drifting among the stars. And this beauty, though it seems surreal, has an incredibly elegant scientific explanation. It is the language of carbon. Recall that a comet's nucleus does not just contain water ice. It is a complex mixture of different kinds of ices, with organic compounds trapped inside. These organic compounds are essentially molecular chains built on a carbon skeleton. Carbon, the element of life, is also a key ingredient of comets. When the warmth of the sun heated the surface of 3I Atlas, it broke the bonds of these complex organic molecules. This process released simpler molecules into space. One of the molecules most created in this process is a very special one, called dicarbon. The name sounds scientific, but it is simply two carbon atoms bonded together. See, 2, a humble molecule, but it is the artist behind this light show. Here is how it works. Imagine a tiny dicarbon molecule floating in the coma. A particle of light from the sun, a photon, flies in and strikes it. The dicarbon molecule absorbs the photon's energy and becomes excited. It's like stretching a guitar string, but it cannot hold that high energy state forever. Nature always seeks balance, a lower energy state. So almost immediately, the dicarbon molecule releases that excess energy. It plucks its own string and emits a photon of light of its own. And here is the miracle. The photon that the dicarbon molecule emits has a very, very specific energy and wavelength. It emits light primarily in the green and blue part of the light spectrum. This phenomenon is called resonant fluorescence, a delicate dance of absorption and emission. Now, multiply that dance by trillions upon trillions of times. The entire coma of 3I Atlas was filled with these tiny dicarbon molecules. All of them were dancing in unison under the sunlight, absorbing a photon, emitting a blue photon. Absorb, emit. Absorb, emit. The brilliant blue light we saw was the combined light from this grand symphony of trillions of molecular dancers. It was a song sung by carbon. The truth is, many comets have a green or blue hue for the same reason. This is a familiar mechanism, but the intensity and the deep blue shade of 3I Atlas suggested it was exceptionally rich in carbon compounds. Its powerful outburst of activity had released a tremendous amount of dicarbon into its coma. creating a more spectacular color display than usual. It was like a singer with a familiar vocal quality, but who sings with extraordinary power and emotion. And this once again reinforces its image as a familiar beauty. That blue color, as mysterious as it seemed, was an affirmation of the physical laws we already know. It was an explainable phenomenon, a beauty built on a foundation of logic and order. It was not an unsolvable mystery. It was an answer, presented in the form of art. And we have seen the familiar nature of Three-Eye Atlas, an active comet. We have marveled at its blue song, a beauty explained by the elegant laws of physics. And now, we will look at the final element, the one that cements its image as a messenger of order. Its path, a path that was entirely predictable. Although Three-Eye Atlas came from a distant and unknown place, the moment it entered our solar system, it began to obey long-established laws. It began a dance with one single powerful partner, our sun. And this dance was governed entirely by an invisible yet irresistible force, gravity. Astronomers since the time of Isaac Newton have understood this dance very well. They can calculate the orbits of planets, asteroids, and comets with astonishing precision. They can predict where Jupiter will be in 100 years, or when a comet will return, all thanks to a deep understanding of the laws of gravity. And when they applied these laws to Three-Eye Atlas, everything matched perfectly. Its hyperbolic orbit, that one-way path, was not a mystery. It was the predictable result of its initial speed and the pull of the sun. Scientists were able to accurately model its path as it passed through the solar system, the point where it would come closest to the sun, and the path it would take on its way out. There were no surprises, no unexplainable deviations. Imagine you are watching a professional javelin thrower. You may not know exactly where the javelin will land, but you know it will fly in a beautiful parabolic arc, obeying the laws of air resistance and gravity. Three-Eye Atlas was the same. It moved gracefully and predictably, precisely as an object influenced only by gravity should. It was like a ball thrown through the cosmos, and it followed the exact path we would expect. This predictability is profoundly important. It shows us that the physical laws we observe here, in our home, are the same physical laws at work everywhere else. They are universal. A visitor from another star system still must obey the same set of rules. The universe, as chaotic and vast as it may seem, is governed by a deep and consistent order. And in that order, there is a sense of peace. And so, our portrait of the familiar is complete. Three-Eye Atlas is a textbook comet with an explainable beauty and a predictable path. It is an open book, a lesson in astrophysics elegantly presented in the sky. It is an affirmation that even visitors from the most distant places can carry a sense of the familiar. Hold this image firmly in your mind, the image of order, of logic, of a universe that operates according to laws we can understand. Let this feeling of safety and familiarity settle in, because now we are leaving this safe harbor. We will begin a new journey into an entirely different sea, where the familiar maps are worthless where the rules seem to bend, where familiarity gives way to strangeness. Now, it is time to meet the first visitor. It is time to step into the mystery of Oumuamua. Our story now turns back in time. Our story now turns back in time, before 3 Atlas, even before Tuai Borisov, to the year 2017, when the idea of interstellar visitors was still a theoretical concept, a possibility discussed by scientists, but never before witnessed. And like our previous story, this one also begins in Hawaii, but with a different telescope and an entirely different feeling. This is not the story of a familiar beauty. This is the story of an anomaly. On the night of October 19th, 2017, a telescope named Pan-STARRS-1 was also carrying out its mission of scanning the night sky. Like Atlas, it searched for moving points of light, near-Earth asteroids, and on that night, it detected something, an extremely faint point of light, moving at an incredible speed. At first, astronomers assumed it was just a small, ordinary asteroid. They gave it a temporary designation, A2017 U1, but as they began to calculate its orbit, a sense of confusion began to set in. The numbers didn't add up. This object was not moving like anything they had ever seen in the solar system. Its orbit wasn't just hyperbolic, it was extremely hyperbolic. It came from a very strange angle in the sky, from the direction of the constellation Lyra, and was hurtling through the solar system with far too much velocity. In that moment, astronomers came to a stunning realization. This was not a member of our family. For the first time in history, humanity had definitively confirmed the existence of a visitor from interstellar space. Excitement spread quickly, but it was mixed with a sense of urgency, because unlike 3I Atlas, which was discovered on its way in, this object was discovered after it had already passed its closest point to the sun and was on its way out. It was like realizing a strange guest was in your house, only after they had already walked through the living room and were stepping out the back door. The window for observation was incredibly short. The entire astronomical world raced against time, pointing every available telescope at this fading streak of light to gather as much data as possible before it vanished forever. And since this was the very first visitor, it needed a special name. The astronomical community decided to honor the place of its discovery. They chose a name from the native Hawaiian language, Oumuamua. The name is made of 2 parts. Omu means to reach out, and mua, in this context, means first or in advance. Combined, Oumuamua carries a beautiful and poetic meaning, the first messenger from a distant place, a perfect name for a historic event. It wasn't a cold designation. It was an acknowledgement of its role as a messenger, the first scout from another world. But the message this scout carried was anything but clear. As scientists began to analyze the scarce data they had collected, the story did not become clearer, it only became stranger. This is where our story shifts from a scientific discovery into a cosmic detective film. And the first piece of evidence, the first clue to its strangeness, came from its light. In astronomy, light is everything. Light is the messenger, the only witness to events that happen millions or billions of kilometers away. We could not touch Oumuamua. We could not weigh it. All we had were the faint photons of light it reflected back, a message written in shimmer. And as scientists read this message, they discovered something completely unprecedented. Here's the problem. Oumuamua was so far away and so small that even in our most powerful telescopes, it was just a single point of light, a single pixel. We could not take a picture of it to see its shape. So how could we possibly know what it was shaped like? The answer lies in how the brightness of that single point changed over time. Imagine you are looking at a small mirror from a great distance in a dark room. If that mirror is round and it is spinning, the amount of light it reflects toward you will be nearly constant. It will always be a steady point of light. But what if that mirror is shaped like a needle and it is tumbling end over end like a baton? When the long side of the needle is facing you, it will reflect a lot of light. You will see a bright flash, but when it turns and only the sharp tip of the needle is pointing at you, it will reflect very little light. The point will almost disappear. By measuring this change in brightness, you can deduce that the object is very long and very thin, and that is precisely what astronomers observed from Oumuamua. Its brightness changed dramatically over a cycle of about 7 to 8 hours. It would get brighter and then dimmer by a factor of 10. This variation in brightness was greater than for any asteroid or comet we have ever observed in our solar system. To produce such a massive change in brightness, Oumuamua had to have a truly extreme shape. It could not be a sphere or a typical lumpy cosmic potato. The computer models showed that to match the data, its length to width ratio had to be enormous, perhaps 5 to 1, 6 to 1, or even 10 to 1. It was at least 10 times longer than it was wide. Picture that. If it were as long as a football field, it would be only as wide as the halfway line. If it were as tall as a skyscraper, it would be only as wide as a car. This was a shape never before seen in nature for an object of its size. Asteroids and comets in our solar system rarely have a ratio greater than 3 to 1. They tend to be more rounded due to random collisions from all directions over billions of years. But Oumuamua was different. It was unnaturally elongated. The most common image artists have rendered is of a cosmic cigar, a long dark red rock tumbling through space. But that is only one possibility. Another possibility, even stranger, is that it wasn't cigar-shaped. It could have been extremely thin. It might have had the shape of a pancake or a disc, very wide but very flat, or even a sheet as thin as a sail. Such an object, when spinning, would also produce a similar change in brightness. We don't know for certain what its true shape was, but we know one thing for sure: it was not normal. Let's make a direct comparison. 3 Atlas was presumed to have an irregular shape, like an ice mountain, a completely familiar form. Oumuamua was more like a needle or a sharp shard, a shape that challenges our understanding of how natural objects are formed. How could such an object be created in nature? Some hypotheses suggest it could be a fragment ejected from a planet or a larger body, torn apart by the tidal forces of a star. This process could potentially create long, thin shards. But these are still just guesses. The mystery of its shape was the first clue, the first piece in a puzzle that was becoming more and more perplexing. It was a warning from the cosmos that not everything out there follows the patterns we are used to. This first messenger did not take the form of a familiar friend. It took the form of a stranger, a complete stranger, and as scientists continued to analyze the data, they discovered that its strangeness did not end with its external shape. It also lay in its very essence, in its mysterious silence. The unusual shape of Oumuamua was already a great puzzle, a needle or a pancake drifting among the stars. But when scientists pointed our most powerful telescopes at it, they weren't just looking for its shape. They were looking for a sign of life in the cometary sense. They were looking for a coma, a tail, any sign that it was breathing out gas and dust under the heat of the sun. And what they found was silence, a silence even more mysterious than its shape. Recall Thry Atlas. When it entered the solar system, it announced its presence brilliantly. It grew a vast coma, a blue halo visible from hundreds of millions of kilometers away. It unfurled two magnificent tails, like a banner of ice and dust. It sang its song. That is the behavior we expect from a dirty snowball. When it approaches a flame, it must melt. It must sublimate. Scientists fully expected Oumuamua to do the same. In fact, its orbit took it even closer to the sun than the orbit of Mercury. It was subjected to extreme heat. Any ice on its surface, water, ice, carbon dioxide, ice, nitrogen ice, should have vaporized violently. It should have had a coma. It should have had a tail. But it didn't. The Spitzer Space Telescope, one of our most sensitive instruments for detecting carbon-based molecules, stared at Oumuamua, and it saw nothing. Not the slightest trace of carbon monoxide or carbon dioxide, the most common gases that escape from comets. Ground-based telescopes also searched for any sign of dust. And again, nothing. Oumuamua was completely inert, completely silent. It was like seeing an iceberg drift into tropical waters, but without it melting, without a single wisp of steam rising from it. This was deeply puzzling. It posed a fundamental question. If it wasn't an active comet, then what was it? The most logical answer seemed to be that it must be an asteroid, a dry, barren rock made of stone and metal. An asteroid would have no ice to sublimate, so it would have no coma or tail, even when very close to the sun. This seemed to solve the problem, but it opened the door to another, even bigger problem. Most models of how star systems form suggest that the objects ejected into interstellar space should overwhelmingly be comets, because they form in the outer peripheries of a star system, where gravity is weaker, and they are more easily influenced by giant gas planets. Rocky asteroids form much closer to their star, where gravity is stronger. Ejecting an asteroid from a star system is much, much harder. Scientists estimate that for every one interstellar asteroid, there should be hundreds or even thousands of interstellar comets. So why was the very first visitor we ever met, the incredibly rare one, It's like visiting a forest for the first time, and the first creature you encounter is not a bird or a squirrel, but a unicorn. It doesn't mean unicorns don't exist, but it is extremely unlikely. Furthermore, the color of Oumuamua was also peculiar. It had a dark red hue, not the gray of rock, but an organic red. This color is often created when carbon-rich organic compounds are irradiated by cosmic rays over a very long time. This suggests its surface might have been covered by a thick layer of organic material, like a protective crust. But if it had so many organic compounds, why didn't they vaporize and create gas? The silence of Oumuamua was a silence full of contradictions. If it was a comet, why was it not active? If it was an asteroid, why was it the very first visitor? And why did it have an organic red color? Every explanation seemed to lead to a dead end. Let's place these two portraits side by side again. Thriatlas arrived like an opera singer, belting out its song loudly and brilliantly for the whole world to hear. Oumuamua arrived like a Zen monk, passing through our world in absolute silence. One was an explosion of life, the other the stillness of a relic. And this silence, this lack of activity, made the next clue all the more shocking, because although it was silent, it was not still. It moved in a way that could not be explained. We are now at the heart of the maze. We have an object with an impossible shape, a needle or a disc tumbling through space. We have a profound silence, an icy body that refused to melt under the heat of the sun. Each clue seems to contradict the last, but the final clue, the last piece of evidence gathered from its faint fading photons, was what transformed Oumuamua from a mere curiosity into one of the profound mysteries of our time. It lay in the way it moved. I recall Three-Eye Atlas. Its path was perfectly predictable. It moved precisely as an object influenced only by gravity should. It was a perfect example of celestial mechanics, a graceful and law-abiding dance with the sun. Scientists expected Oumuamua to do the same. They calculated its hyperbolic orbit with extreme precision, based on the only force they knew to be at play, the gravitational pull of the sun, the planets, and other celestial bodies. They predicted exactly where it should be at any given moment, but it wasn't there. As astronomers with the Hubble Space Telescope continued to track Oumuamua on its way out of the solar system, they detected a small but unmistakable deviation. Oumuamua was not slowing down as much as it should have. It was moving slightly faster than gravity alone could explain. It's like throwing a stone into the air. You expect it to go up, slow down, and then fall back. But this stone, after reaching its peak, didn't fall back as quickly as expected. It seemed to linger a little longer, as if a gentle, invisible push was counteracting the pull of gravity. This acceleration was extremely small, only about 0.001%. But in the precise world of celestial mechanics, it was a colossal difference. It was a clear signal that a second force, beyond gravity, was acting on Oumuamua. So, what was that force? For a normal comet like Three-Eye Atlas, The answer is simple. Outgassing. As the ice on a comet's surface sublimates, it shoots out jets of gas and dust, like small, uneven rocket engines. These jets create a gentle thrust that can slightly alter the comet's trajectory. This is a well-known phenomenon observed in hundreds of comets. Was this the explanation for Oumuamua? The problem is, to create a push strong enough to explain Oumuamua's acceleration, it would have had to vent a huge amount of gas and dust. And so we returned to the second mystery. We looked very closely, and we saw absolutely nothing. Not a trace of gas, not a hint of dust. It was accelerating with no visible engine. This is the heart of the mystery. It has an unexplainable shape. It has an unexplainable silence, and it has an unexplainable acceleration. All three combined create a nearly perfect puzzle. Every natural explanation seems to fail on one of these three facts. If you say it's a comet to explain the push, you cannot explain why it was silent. If you say it's an asteroid to explain the silence, you cannot explain why it had a push. And whatever it was, you struggle to explain its bizarre shape. Let's place these two final images side by side. 3i Atlas moved like a ball thrown through gravity, a smooth and predictable arc. Oumuamua moved like a sailboat catching a wind we cannot see, an invisible cosmic wind, strong enough to push a rock hundreds of meters wide, yet so subtle that it left no trace. This anomalous push is what forced some scientists to begin thinking outside the box. It forced them to ask a question that previously belonged only to science fiction. If there is no natural explanation, that perfectly fits all the evidence. Then, could there be an unnatural one? This is where our story steps into a land of speculation, of bold possibilities, and of a scientific debate that will continue for years to come. We are standing at a fork in the road. On one side are the laws of physics we know and trust. On the other is a set of evidence that seems to challenge those laws. Oumuamua has left us with a riddle, a strange shape, a profound silence, and an invisible push. Before we explore the most audacious ideas, science demands that we do everything we can to find a natural explanation. And in that effort, scientists have put forth some incredibly creative hypotheses. The first hypothesis attempts to solve the biggest contradiction. How can an object have the push of a comet without a visible coma? Remember, the core problem was the silence. Our telescopes detected no gas or dust, but not detected doesn't quite mean not there. It just means we didn't detect the kinds of gas and dust we typically look for, like carbon monoxide, carbon dioxide, or silicate dust grains. So what if Oumuamua was outgassing something that our telescopes were not designed to see? Something that is completely transparent. This is the foundation of a very clever hypothesis proposed by scientists Daryl Seligman and Gregory Laughlin. They asked the question, could Oumuamua have been made of solid hydrogen ice? Hydrogen is the most abundant element in the universe. It makes up about 75% of all normal matter by mass, but we usually think of it as a gas, like in the sun or the giant gas planets. For hydrogen to exist as a solid ice, It needs an extremely, extremely cold environment, far colder than what's needed to freeze water or carbon dioxide. Scientists believe that such hydrogen icebergs could possibly form in the cores of giant molecular clouds, the coldest stellar nurseries in the galaxy. So, why is this hypothesis so appealing? Because it elegantly solves the problem of the silence. When solid hydrogen ice is warmed, it sublimates and turns into hydrogen gas. And molecular hydrogen gas, H2, is almost completely transparent. It does not efficiently emit or reflect light in the wavelengths that our telescopes were observing. So, according to this hypothesis, Oumuamua was an active comet. It was spewing out a huge amount of gas as it neared the sun, and it was these invisible jets of hydrogen gas that created the anomalous push we observed. It had a thrust, but no visible coma, because that coma was made of a ghost gas. It was the ghost of a comet. This hypothesis might also partially explain its strange shape. The sublimation of hydrogen ice would be very rapid and uneven, potentially eroding an original iceberg into a long, thin shape, like a bar of soap worn down by a stream of water. It is a natural explanation. It is elegant, and it comes from known physical principles. It does not require us to invoke extraordinary ideas. However, like any good hypothesis, it has its own problems, and these problems are quite significant. First, no one has ever observed a hydrogen iceberg in nature. They remain a theoretical concept. Second, hydrogen ice is extremely volatile. It would sublimate even under the faint starlight of interstellar space. A hydrogen iceberg the size of Oumuamua could not survive a journey of hundreds of millions or billions of years. It would have completely evaporated long before it ever reached our solar system. It's like trying to send an ice cube across a desert. It simply would not arrive intact. To solve this problem, some scientists have suggested that perhaps Oumuamua was much younger than we think. Perhaps it came from a very nearby star system and had only just begun its journey. But this contradicts the observed density of interstellar objects. So, the hydrogen comet hypothesis, while very appealing, remains an open question. It is an admirable effort of human ingenuity to try and find a natural explanation for something strange. It shows that the universe may contain types of objects we have never before imagined, but it is not yet a complete answer, and so the search must continue. The hydrogen comet hypothesis opened the possibility that Oumuamua was made of a strange type of matter we had never seen. But what if the answer lies not in a new type of matter, but in a new origin? What if Oumuamua was not a primordial comet formed from a protoplanetary disk, but a fragment from a world that once was? This is the foundation of the second natural hypothesis, a story of destruction and rebirth. The story of the planetary shard. This hypothesis, proposed by scientists Alan Jackson and Stephen Desch, starts from a very different idea. Instead of trying to explain why Oumuamua was silent, they started with the anomalous push. They ask themselves, is there another type of ice besides hydrogen ice that could create a thrust without leaving a dusty trail and yet be durable enough to survive a long journey? And they found a very interesting candidate. Solid nitrogen ice. Nitrogen is a very common element. Our own Earth's atmosphere is nearly 80% nitrogen gas. In the extremely cold reaches of the outer solar system, nitrogen can freeze into a solid ice. We know this for a fact. The surface of Pluto is covered in vast glaciers of nitrogen ice. So is Neptune's moon Triton. Nitrogen ice has a very important property when it sublimates. It turns into transparent nitrogen gas. It does not produce dust. This fits perfectly with the silence of Oumuamua. It could have been outgassing a large amount of nitrogen gas, creating the push that we could not see. And unlike hydrogen ice, nitrogen ice is much more durable. It does not easily vaporize in interstellar space. A nitrogen iceberg could easily survive a journey of hundreds of millions of years. This hypothesis seems to solve both major problems, the push and the silence. But it raises an entirely new question. How could a solid chunk of nitrogen ice come to exist on its own in interstellar space? We do not see nitrogen comets forming naturally, and this is where the story becomes dramatic. Jackson and Desch proposed that Oumuamua was not a comet formed from scratch. They proposed that it was a shard broken off from the surface of a distant planet, a planet much like Pluto. Picture this scenario. In a distant star system, there is an icy dwarf planet. Orbiting at the edge of its system, its surface is covered in nitrogen ice. About 500 million years ago, another object, perhaps a comet or an asteroid, slammed into that planet. The incredibly powerful impact ejected a massive fragment from the planet's nitrogen ice crust. That fragment was thrown into space with enough velocity to escape the gravity of its parent star and begin its own interstellar journey. This hypothesis explains a great deal. It explains the nitrogen ice composition. It also explains Oumuamua's strange shape. As this shard traveled through space, starlight and cosmic rays would slowly erode it. This process, according to their calculations, would naturally flatten the fragment over time. It would be worn down into a shape resembling a pancake or a well-used bar of soap, an extremely flat shape, perfectly consistent with the light variations we observed. So here we have an almost perfect story, a fragment of an exopluto made of nitrogen ice eroded into a pancake shape, which flew into our solar system, outgassed transparent nitrogen gas to create its thrust, and then continued on its journey. Every piece of the puzzle seems to fall into place. However, science always demands rigor. This hypothesis, as elegant as it is, has also faced criticism. Some scientists argue that for there to be enough nitrogen shards wandering the cosmos for us to accidentally encounter one, there would have to be an extremely large number of Pluto-like planets out there, more than our current models predict. Furthermore, the hypothesis requires a rather large coincidence. The shard had to be eroded just enough to have that flattened shape at the exact moment it entered our solar system. Despite this, the planetary shard hypothesis remains one of the leading and most robust natural explanations for the Oumuamua mystery. It is a testament to the creativity of scientists, their ability to connect clues from different fields to weave a coherent narrative, and it also carries a beautiful philosophical meaning. It suggests that even distant worlds can be wounded. They too can be broken, and those broken pieces can begin a new life, a new journey, carrying the legacy of the world that made them. Oumuamua could be such a legacy, a frozen memory of a world that was once scarred. We have now explored two paths of reason: the path of a new kind of matter, the ghost of hydrogen, and the path of a new kind of origin, the frozen legacy of a shattered Pluto. Both are admirable attempts to explain the strange within the framework of what we consider to be natural. But both of them face difficulty, unanswered questions, and this has led some scientists to a third fork in the road, a path less traveled, a path that requires openness and the courage to think differently. This is not a path of assertion, but a path of inquiry. The question is this: if all natural explanations do not quite fit, then could there be an unnatural explanation that fits better? This is where we listen to the whisper of Avi Loeb. Avi Loeb is a reputable theoretical astrophysicist and the former chair of the astronomy department at Harvard University. He is not a person who seeks sensational stories. He is a scientist guided by data, and when he looked at the data from Oumuamua, he came to a different conclusion. He applied a principle known as Occam's razor, the principle that the simplest explanation that fits all the evidence is often the correct one. Let's review the evidence one more time through this lens. Evidence 1. An extremely flat shape like a pancake or a thin sheet. Evidence 2. A complete lack of any detectable outgassing, no coma, no tail. Evidence 3. A slight non-gravitational push. The natural hypotheses we've examined must add very special conditions to try and explain this trio. A never-before-seen hydrogen iceberg, or an extremely rare planetary collision scenario. Professor Loeb asked a different question. Is there any type of object that we have already conceived of that would naturally possess all three of these properties? And he found an answer: a light sail. A light sail, also known as a solar sail, is a technological concept that we humans are developing ourselves. It is an extremely thin and large membrane made of a reflective material. It works like the sail of a ship at sea, but instead of catching the wind, it catches the wind of light. Light is made of particles called photons. Although they have no rest mass, photons have momentum. When trillions upon trillions of photons from a star strike the surface of a light sail, they transfer a tiny bit of their momentum, creating a gentle but constant push. This push can slowly accelerate a spacecraft to incredible speeds over time without carrying any fuel. Now, let's see how a hypothetical light sail fits the evidence of Oumuamua. Regarding the shape, by definition, a light sail must be extremely thin with a large surface area. A shape like a pancake or a thin sheet is its optimal form. This perfectly matches the first piece of evidence. Regarding the silence, a light sail is made of solid materials, like metal or composites. It contains no ice. Therefore, it would not outgas when approaching a star. It would be completely silent. This perfectly matches the second piece of evidence regarding the push. A gentle, non-gravitational push is precisely how a light sail operates. The push from the sun's photons could exactly explain the small acceleration we observed. This perfectly matches the third piece of evidence. According to Avi Loeb's hypothesis, the simplest explanation, the one that doesn't require us to invent new types of comets or rare collision scenarios, is that Oumuamua was not a rock or an iceberg. He argues that its characteristics are most consistent with an object of technological origin. It is crucial to clarify here that this is a scientific hypothesis, not a definitive statement. Professor Loeb is not saying Oumuamua was a crude starship. He is proposing that it could be a technological relic. Perhaps it was a defunct light sail, a piece of high-tech space debris, drifting through space long after the civilization that created it has vanished. Or perhaps it was a type of probe sent to gather data, much like our own Voyager probes. Its purpose we cannot know. This hypothesis, as might be expected, has ignited an intense and incredibly important debate within the astronomical community. The majority of scientists maintain a healthy skepticism. They argue quite reasonably that we should not jump to extraordinary conclusions without extraordinary evidence. A natural explanation, even if we haven't found it yet, is still statistically more plausible. They argue that invoking an extraterrestrial civilization is too great a leap, and science should not operate on such leaps. And that debate is the very beauty of science. Science advances not just through answers, but through the right questions. And Oumuamua has forced us to ask the biggest questions of all. The purpose of presenting this hypothesis here is not to convince you that it is true. It is to complete the portrait of Oumuamua as an anomaly that has pushed the boundaries of our understanding and our imagination. It has forced us to be humble. It has shown us that, after centuries of observing the heavens, there are still things out there that can make us pause and say, we don't know for sure. And in those three words, don't know for sure, there is a profound magic. It is the open door to all future discovery. We have traveled through the maze of hypotheses, from the ghosts of hydrogen to the fragments of lost worlds, and even ideas that lie at the edge of imagination. And perhaps we will never have a final answer to the mystery of Oumuamua. It has traveled too far, carrying its secrets into the endless dark. But perhaps the purpose of these visitors is not to bring us final answers. Perhaps their purpose is to teach us lessons. And in this final chapter, we will contemplate the two great lessons that these two visitors have left behind. Namwara, let us begin with the lesson of the familiar, the lesson from 3i Atlas. Let us return to our third traveler, 3i Atlas, the messenger of ice and light. After the confusion and the difficult questions left by Oumuamua, the arrival of Atlas was like a gentle rain shower after a hot summer day. It brought a sense of relief, a sense of peace, because the first and most important lesson that Atlas taught us was a lesson in universality. It showed us that The laws of nature that we observe here, in our own small home, are the same laws at work in the most distant places. It was a comet, and it behaved exactly like a comet. It was made of ice and dust, materials we know very well. It sublimated under the heat of the sun, creating a coma and a tail. According to physical processes we can describe with mathematics, its brilliant blue color, as magical as it seemed, was the result of a familiar molecular dance of carbon, and its path was perfectly governed by Newton's law of universal gravitation. Why is this so important? Because it shows that we are not an anomaly. Our solar system is not a special oasis with its own set of rules. We are part of a larger cosmos, a cosmos that is consistent and orderly. It is like traveling to a distant land and realizing that though the language and culture may be different, the fundamental human emotions, like love, sorrow, joy, remain exactly the same. Atlas showed us this on a cosmic level. The recipe for making a comet in its home star system was not so different from the recipe here. This lesson brings a profound sense of connection. It makes the vast and seemingly intimidating universe a little more familiar, a little more understandable. It tells us that we can use our knowledge to understand what is happening in places we can never hope to set foot. Science is a universal language, and in that universality, there is a beauty and a comfort. It's like a whisper from the cosmos saying, "You are on the right path. What you have learned is real. Keep exploring." 3i Atlas was an affirmation, a confirmation that order exists amidst the chaos. It is the solid foundation, the safe ground we can stand upon before we look up at the greater mysteries. That is its legacy, a gift of clarity and familiarity, a reminder that even visitors from the most distant places can bring with them a sense of home. If 3i Atlas brought us the comfort of an answer, then Oumuamua brought us a completely different gift, a more difficult gift, but perhaps an even more precious one, the gift of a question. The second lesson is a lesson in humility. Oumuamua arrived and gently shattered many of our assumptions. It was like a strange wind blowing through a tidy room, disturbing everything. It challenged our understanding of how natural objects form, with its impossible shape. It challenged our understanding of cometary behavior, with its mysterious silence. And it challenged our understanding of the laws of motion, with its invisible push. The lesson Oumuamua teaches us is a lesson that science must always remember. We do not know everything. The universe is under no obligation to fit into the neat little boxes we have created for it. It is always bigger, stranger, and more diverse than we can possibly imagine. Oumuamua is a reminder that just because we have never seen something before does not mean it cannot exist. We had never seen a natural object with a 10-to-1 ratio, but Oumuamua existed. We had never seen a comet that was inactive at such a close distance, but Oumuamua existed. We had never seen an object with a thrust but no outgassing, but Oumuamua existed. It is an anomaly, and in science, anomalies are the most precious things of all. because they are where real discovery happens. They are the cracks in the wall of our knowledge, where the light of a new understanding can shine through. Oumuamua forced us to stretch our imagination. It pushed scientists to conceive of entirely new types of objects, like hydrogen comets, or new formation scenarios, like the fragments of shattered planets. And it also opened a dialogue, in a serious and scientific way, about the possible existence of technological relics out there. It made an idea that was once taboo into a valid scientific question. The lesson from Oumuamua is a lesson in openness. Be ready for the unexpected. Be ready to admit that our models may be incomplete, and always keep a curious mind. A mind that is willing to ask questions, even when those questions seem difficult or uncomfortable. It is a warning against intellectual arrogance. It whispers to us that you have learned so much, but an entire ocean of the unknown still awaits. And that is a profoundly important message. Oh, we have a lesson in the familiar and a lesson in the strange. On one side, three-eyed Atlas, an affirmation of the order and universality of the cosmos. On the other, Oumuamua, a reminder of the mystery and the limits of our knowledge. They seem like two opposite extremes. One is an answer, the other is a question. But perhaps the greatest lesson, the final lesson, lies not in either one. It lies in the existence of both. The final lesson is a lesson in balance. Imagine the universe as a giant book. If every interstellar visitor we met were like Three-Eye Atlas, if everything were familiar and explainable, that book would become boring. We would quickly conclude that we understand almost everything. Science might become complacent. Our curiosity might fade. We would have order, but we would lack wonder. Conversely, if every visitor were as mysterious and anomalous as Oumuamua, if nothing followed the rules we know, that book would become chaotic and incomprehensible. Science would become powerless. We would have no foundation to stand on. Every new discovery would only add to the confusion. We would have wonder, but we would lack understanding. The truth is, the universe sent us both. It sent us Atlas to say, what you have learned is true. Your foundation is solid. And it sent us Oumuamua to say, but never think that foundation is everything. There are still so many floors you have never seen. One reinforces our knowledge, the other fuels our imagination, and we need both. Science, much like life, thrives in the balance between order and chaos, between the known and the unknown. Atlas is the firm ground beneath our feet. Oumuamua is the distant stars we look up to, and we stand in the middle, with our feet on the ground and our eyes on the sky. This final lesson is a lesson in diversity. The universe is not a monolith. It does not create only one type of comet. It does not create only one type of object. It is a zoo of infinite possibilities. There are familiar things. There are strange things. There are things in between. And there are things for which we do not even have words yet. And that is a wonderful thing. It ensures that our journey of discovery will never end. There will always be a familiar beauty to comfort us, and there will always be a new mystery to challenge us. That is the legacy these two visitors have left behind, a complete symphony, made of both the notes we recognize and the notes that make us stop and listen closely. And so, the silent dialogue between the two travelers comes to an end. They arrived, they told their stories, one with words and one with silence, and then they resumed their journeys. Returning to the ocean of silence from which they came, they leave us here on our tiny island with their precious lessons. 3 Atlas came as a storyteller, carrying a tale we could understand, a story of order, of universal laws of a cosmos that, while vast, is still predictable. It was an affirmation. Oumuamua came as a Zen poet. It did not offer a clear story. It left us with a koan, a riddle with no easy solution, a great question. It was a doubt, and perhaps we need both. We need answers to build our foundation of knowledge, to feel safe and confident in our understanding. But we also need the great questions, the unexplainable mysteries, to keep our curiosity alive, to push us, to keep searching, to keep us humble. The true legacy of Oumuamua does not lie in what it was. Was it a nitrogen iceberg, perhaps? Was it a hydrogen comet, possibly? Was it a technological relic? We have no evidence to say so, but we also cannot completely rule out the possibility. Its true legacy is that it forced us to ask. It forced us to admit that the universe does not always conform to our expectations. It gave us a gift, the gift of wonder. Good night, wish peace in mystery. Thank you for contemplating these 2 encounters with cosmic drift. Thank you for taking the time to listen to both the answer and the question. As you fall asleep tonight, let your mind be at rest in the perfect balance between the known and the unknown. Accept that not everything in life or in the universe needs an immediate answer. Sometimes the greatest peace doesn't come from finding the answer. It comes from learning to live in harmony with beautiful questions. Let your curiosity dissolve into relaxation. Let the mysteries of the cosmos become the glittering stars in your dreams. I wish you a truly peaceful night and dreams full of beautiful questions.